Are you really sitting still right now? I mean, you probably feel completely at rest as you're taking this in. But think about it from the perspective of an astronaut looking down from outer space. To them, you're actually spinning at thousands of miles an hour right along with the Earth. It's a pretty wild thought experiment, isn't it?
Well, welcome to The Explainer. Today we're putting you right in the passenger seat for a road trip to uncover some fundamental, everyday laws of physics. We're going to dive into kinematics, and we're going to do it in a way that just makes absolute sense.
Okay, let's take a quick look at our roadmap for today. We've got 1. The illusion of rest. 2. Distance versus displacement. 3. Speed, velocity, and direction. 4. Uniform versus non-uniform motion. And finally, 5. The rate of change.
So starting with stop number 1, the illusion of rest. We buckle up, we start the engine, but honestly, before we even move an inch, it's super important to realize that motion completely depends on your reference point. In physics, a body is considered at rest if its position doesn't change compared to a specific reference point, like, say, a stationary tree outside or a railway station. But if its position does change compared to that point, well, then it's in motion.
And that brings us to the absolutely crucial golden rule of kinematics. Rest and motion are not absolute, they are completely relative. For instance, imagine a mother riding in a car. To her, her son sitting right next to her in the passenger seat is perfectly at rest. But to a person standing outside on the side of the road, that exact same boy is zooming by.
The actual state of the boy literally changes based entirely on who is doing the observing. It's just like if a group of students observed each other from inside versus outside a moving vehicle, they're going to see completely different realities. It really is all relative.
Moving right along to section 2, distance versus displacement.
All right, our road trip is officially underway. Now, the big takeaway here is understanding the stark difference between two everyday words. Think of distance as the actual, winding physical road your tires touch, the total length of the path you traveled. But displacement, that's a bit different. That is simply the shortest, straight-line distance from your initial starting position to your final ending position.
To make this super practical, let's compare the two. Your car's odometer, that little running ticker on the dashboard, tracks the total distance. It measures every single twist, turn, and random detour you take. But if you laid a physical map out and placed a perfectly straight ruler from your starting point to your destination, that straight line measurement gives you your displacement.
Let's categorize our physics toolkit really quickly. Basically, we have two types of quantities. Scalar quantities, like distance, speed, and time, only care about magnitude. They don't care about your direction at all. Vector quantities, on the other hand, like displacement, velocity, and acceleration, they absolutely care about the magnitude plus the specific direction you're heading in.
So, here is a quick mind bender to prove the point. If you drive 2 kilometers from your house to school and then 2 kilometers straight back home, your total distance traveled is 4 kilometers, but your total displacement, it is exactly 0 because your starting position and your final position are the exact same place. Crazy, right?
All right, section 3, speed, velocity, and direction.
We are making really good time on the road, so let's glance at the speedometer. Now, while speed tells us how fast we're crushing those kilometers over time, it's just a scalar quantity. Velocity, however, tells us our speed plus our compass direction. So 40 kilometers per hour is a speed, but 40 kilometers per hour heading straight northeast, now that is a velocity.
Oh, and if you're ever doing calculations for this kind of stuff, our sources provided this brilliant, secret math shortcut, the fraction 5/18. If you ever need to quickly convert your car's speed from kilometers per hour into the standard scientific unit of meters per second, literally just multiply by 5/18. Boom! It saves you from doing all those messy, annoying conversions with thousands of seconds.
Now, because our speed is constantly fluctuating on a real road trip, stopping for traffic, slowing down to take a turn, we almost never travel at just one single speed the whole time. That's why we use average speed to give people a meaningful single number. You just take the total distance traveled and divide it by the total time taken. Simple as that.
Let's roll right into section 4, uniform V's, non-uniform motion.
Think about the feeling of transitioning from a wide-open, empty highway straight into crowded city traffic. Out on that perfect, empty highway, our car might cover exactly 10 meters every 2 seconds. Covering equal distances in equal intervals of time means we're maintaining a constant velocity. In the physics world, we call this uniform motion.
But let's be real. Reality usually looks quite different. In heavy traffic, we travel unequal distances in equal time intervals. So maybe we move 2 meters in the first second, 10 in the next, and only 4 in the third. Speeding up and slowing down constantly like that is a classic example of non-uniform motion.
And honestly, this perfectly illustrates our daily driving experience. Perfectly uniform motion? It's essentially just an ideal case, something for the textbooks. In everyday life, we almost always experience non-uniform motion. And that's exactly why those tools we just talked about, like calculating average speed, are so incredibly vital to actually making sense of our trips.
And finally, Section 5, the rate of change.
Imagine we finally hit a completely empty stretch of road. The coast is clear and we press down hard on the gas pedal. When we hit that pedal, we experience acceleration. Acceleration is formally defined as the rate of change of velocity with respect to time. Put simply, whenever your velocity changes over time, you are accelerating.
Now, the absolutely crucial point here is that because velocity is a vector, meaning it includes direction, there are actually 3 distinct ways you can accelerate. You can speed up, which is positive acceleration. You can hit the brakes to slow down, which is actually negative acceleration or retardation. Or, get this, you can just change direction by turning the steering wheel. Yep, even at a constant speed, taking a turn means your velocity changed, so you technically accelerated.
Calculating this rate of change is actually just a simple 4-step process. You identify the initial velocity, the final velocity, and the time taken. Then you subtract the initial from the final and divide by time. So if a boy on a bicycle starts from rest, meaning his initial velocity is 0, and he pedals hard to reach 6 meters per second in 30 seconds, his positive acceleration is simply 6 minus 0 divided by 30. That gives us exactly 0.2 meters per second squared.
As our road trip explainer comes to an end, I want to leave you with this final thought, bringing us right back to our starting point. The mind-bending nature of relativity means that next time you look out the passenger window, ask yourself, are you moving forward or is the entire world just moving backward? Depending on the observer, both answers might just be right. Thanks for riding along with me.